Hello, welcome all of you again to this NPTEL online certification course on fundamentals of composites and cellular materials. I am Tapas Laha from Metallurgical and Materials Engineering, IIT Kharagpur. So, today we are going to discuss on boron and carbon fibers. Now, in the last class we discussed the basics of fibers, their basic processing techniques. We also discussed the properties of fibers, and then we started talking about different kind of commercial fibers. The first one which we discussed in the last class was glass fiber. In today's class, I plan to discuss on boron fibers and carbon fibers and basically their synthesis, properties and application. So, let us start talking about boron fiber. Now, if you look at this particular microstructure, what you see here is that it is basically a concave structure, and the boron grains are here either amorphous or nanocrystalline in nature. And an interesting point here is that the boron fiber is basically produced by chemical vapor deposition. That means, you need a substrate on which this boron material could be deposited, and in this case, in this particular structure, just so you can see here is that in this particular fractured surface of boron fiber, you can clearly see there is a core, and on this core boron is getting deposited, and then ultimately you get boron fiber. That is why boron fibers are basically composite fibers with a core made of tungsten. Now, why are we so much interested about boron fiber? Because of its extremely high strength and modulus. If we look at this particular graph, you can see in the last class we discussed about glass fiber. So, you can see in terms of specific compression strength and specific modulus in the x axis, you can see where glass fiber is actually staying. Now, if you look at the boron fiber, you can clearly see that the strength and modulus of boron fiber is quite high than glass fiber. So, we will talk about more on the properties of boron fiber, but now let us talk initially on how we could synthesize boron fiber. So, as I mentioned in the first slide, that boron fibers are basically deposited by chemical vapor deposition, and this CVD is done on a substrate which is basically a tungsten or carbon wire, and the diameter of this tungsten or carbon wire is around 10 micrometer, and on that around 100 to 200 micrometer of boron fiber is deposited. Now, if you look back historically, there are two basic techniques by which boron fibers are synthesized. The first one is basically thermal decomposition of boron hydride, BH3. If you heat it at a higher temperature, then you get boron and hydrogen gas, and this can be deposited on carbon fiber. And the advantage of this process is that the temperature requirement is not very high. However, the problem in this case is that hydrogen gets evolved, and that basically weakens the interface between the substrate and boron. Okay. So, basically we have weak interface and lack of adherence, and that is why this process is not a very good technique to synthesize boron fiber. So, ultimately the second technique, which basically talks about reduction of boron halide, BX3, X is halide. So, BX3 and you reduce it with hydrogen, you get boron and then HX, okay, and it requires a little bit higher temperature than the previous one. So, let us look into the setup by which boron fiber gets synthesized by reduction of boron halide. So, if you look at this particular diagram, you see the CVD chamber, basically it is a tube, and in the tube a tungsten wire is going through the length, and then you have electrodes of mercury which basically heats the tungsten fiber, tungsten wire basically here, tungsten wire, right. And then the input is basically here, you can see the boron halide, in this case BCl3 and hydrogen, and some amount of dopant also could be given, and then ultimately by the reaction, this particular reaction, boron gets deposited on the substrate or on the surface of this tungsten, and this tungsten wire is continuously moving. Okay. So, that means you have to, in terms of synthesizing boron fiber, there has to be a correlation, kind of relationship between the speed of the wire, tungsten wire, and the temperature, okay, and that ultimately will dictate the deposition kinetics of boron on the tungsten fiber, tungsten wire. So, obviously, as you can see here that BCl3, only 10% of that gets converted into boron in this reaction, okay. And the interesting fact here is that the process gives boron fiber at a very high and uniform quality. The question might come in your mind is that why tungsten substrate, why not other material? Tungsten is costly, tungsten is also heavier, okay. And when we try to make some composite material, we try to reduce the weight also, but then why are we choosing tungsten? There are a few reasons. This is a high temperature process, so we should choose a material which can withstand high temperature without any reaction. Tungsten is good for that. Also, you have to make and wire of 10 to 12 micrometer diameter. Tungsten is very good in that sense. So, that is the reason that tungsten wire is used as the substrate. Okay. So, I think now we have a fairly good information or good understanding on how boron fiber could be synthesized by reduction of boron halide. Okay. Now, one important factor, as I was mentioning earlier, is that what is the relationship between the velocity or the wear speed and the temperature, okay? Because in one hand we want to have a very high velocity to increase the production rate. At the same time, you have to allow enough time and temperature so that boron gets deposited on the substrate in enough amount, right. So, we have to take care of this temperature, which is called critical temperature. If you look at this particular graph, this hatched section is basically the zone where you get microcrystalline grains, which is not desirable because of lower strength. You have to remain in this zone where you get amorphous or nanocrystalline boron grains. So, if you look at these particular lines, all these lines denotes the different diameters of boron fiber starting from 25 to 60 micrometer. Now, let us consider one constant temperature 1100 degrees Celsius. So, you can see that at a fixed temperature, if you increase the wear speed, you can clearly see that the deposition amount or basically the diameter of boron fiber gets reduced. Okay. At the same time, at a particular wear speed, you can clearly see here a particular wear speed, let us say this particular 2 meter per minute. Here you can see as you increase the temperature, you can clearly see that because of that increase in temperature, the kinetics, deposition kinetics gets improved, and that leads to higher diameter of boron fiber, synthesis of higher diameter of boron fiber. But then you have to be careful, in that process you should not end up in this zone where you get microcrystalline grain. So, that is basically the important factor here, is that you want to optimize the velocity of the wear and the temperature, but then you have to also be careful so that you do not go into this particular zone where you get microcrystalline boron grains. All right. So, now let us look at the cross section of boron fiber. How does it look? So, from this diagram you can clearly see that you have a tungsten core and then the boron gets deposited. Okay. Now, in this schematic you can see here that you have tungsten core and then boron is deposited on its surface, and then a thin layer of SiC is also made or coated on the surface of boron fiber, and the purpose here is that boron should not react with the matrix material when it is being used as reinforcement fiber. Okay. So, that is why this layer of SiC is deposited on boron fiber. Another interesting fact here is that as this process of boron fiber synthesis is a high temperature process. So, there will be reaction or dissolution, partial dissolution of boron into tungsten, and then ultimately the tungsten, it was around 10 to 12 micrometer, as I mentioned in the beginning. That because of the reaction between boron, the diameter of that core region increases, and this kind of different kind of tungsten boron compound gets formed. Okay. Starting from tungsten to W2B to WB, it depends basically on the availability of boron. So, availability of boron is maximum at the surface, there you get WB4, and then at the core you get W2B depending upon the availability of boron, as I mentioned earlier. So, that is the basic structure and morphology of boron fiber. And as I mentioned earlier, this boron fiber would be having a concave structure. You can clearly see here the grains which are forming here, in the shape or in the morphology of concaves. Okay. So, now let us look into the properties of boron fiber. Okay. As I mentioned earlier, that boron fiber synthesis is a costly process because of the precursor, which is BCl3, and also we are using tungsten wire as the substrate. So, all these are expensive materials, but at the same time if you look at these properties, you can see what kind of strength and modulus can be achieved in boron fiber. So, you can clearly see in the range of 4 GPa strength, which is enormously high. At the same time you also can see the modulus of boron fiber is quite high in the range of 400 GPa. So, because of this high strength, extremely high strength and high modulus, boron fibers are used in exotic applications where you need very high strength, very high resilient. For example, golf shaft. Okay. The shafts are reinforced with boron fibers because of their high modulus, okay, high stiffness. Similarly, these fishing rods, you need very high stiffness, high resilience. So, again you can see in this case of when you need heavy duty fishing rods, their boron fibers are used. Obviously in aerospace industry where again you need a very high strength and modulus, boron fibers are used. So, yes, boron fiber synthesis is costlier. In the earlier case, if you remember, synthesis of glass fiber is not costlier and it gives you moderate kind of strength or modulus, but in case of boron fiber you get extremely high strength and modulus. Obviously, the expenditure of boron fiber synthesis increases many folds compared to glass fiber, and again you can see all these exotic applications where boron fibers are used. All right. So, now I think we have some idea about boron fibers. So, now let us discuss on carbon fiber. Okay. Now, carbon fiber, the interesting part of carbon fiber is that yes, they definitely show very good modulus and strength, and when it comes to specific values, basically when it is, if you compare with density, so density of carbon fiber is quite low, and because of that the specific modulus and specific strength of carbon fiber is very high. But the story does not end there, the advantage does not end there. The advantage, the primary advantage of carbon fiber is that depending upon how you synthesize it, you get wide range of strength and modulus for carbon fibers. So, you can see here in this particular table is that depending upon what kind of precursor means starting material. So, from where you start making the fiber, so depending upon the precursor you can see there are different kind of tensile strength, different range of tensile strength and modulus and elongation. Okay. And as I mentioned earlier, these are lightweight. Okay. Obviously, carbon fibers are very good electrical and thermal conductivity, they show very good electrical and thermal conductivity and low coefficient of thermal expansion. So, the coefficient of thermal expansion is lower, and because of its atomic structure, it does not suffer from stress corrosion of stress rupture unlike glass or polymer fibers, excellent high temperature strength, very important point, and outstanding fatigue resistance. So, now again you can see here the field of application almost in all kind of applications, starting from civil engineering to pressure vessels to marine to automotive to turbines to sports industries to aerospace industries, everywhere there is huge use of carbon fibers. And you can see this data is of 2013. So, basically 10 years old data, and you can see the use of carbon fiber, how much carbon fibers are used annually. It is quite high amount actually. What is the atomic structure of carbon fiber? Okay. We have different allotropes of carbon, but in case of carbon fiber it is basically graphite or graphene sheets. So, you can see here these are the individual graphene layers which are basically attached by van der Waals bonding. Okay. So, the strength in x and y plane is quite high, but in the z direction the strength and modulus is obviously not that high because of the poor or weak van der Waals bonding. Okay. But in the x and y direction, because of sp3 hybridization, the strength and modulus is extremely high. So, the aim would be here when you try to make carbon fiber is that the axially it should be in the x and y direction. Okay. So, that you get extremely high strength. By the way, there is another graphene structure is there, carbon allotropes, and I think you all can recognize this particular structure. It is called Fullerene structure or Buckminster Fullerene structure. Okay. But in our case, we will talk about these graphene sheets being layered in this particular fashion. So, now let us talk about the processing of carbon fibers. Now, we are talking about the first one, the example I am giving here is basically PAN is the precursor. Okay. So, as I mentioned, there are different kind of precursors. The first one I am discussing is PAN or polyacrylonitrile. I am talking about PAN because the PAN based carbon fibers occupies 90% of the carbon fiber market. Okay. Obviously, because of their extremely high modulus and very high strength. Okay. And PAN is basically, if you look at the structure, this is basically CH2CHCN. So, you have a nitrile group CN group attached with CH2CH. Okay. That is the basic structure of PAN. So, what are the different steps of carbon fiber synthesis? Basically, there are 4 steps. The first step is that you take the precursor material, and this precursor material is generally of high molecular weight, okay, long polymeric chain. So, first process step is to, by spinning method, you make fiber of the precursor material, right. It is not the carbon fiber, but the fiber of the precursor material, and that fiber of precursor material goes through 3 steps. The first step is stabilization, second step is carbonization, and third step is graphitization. If you look in this particular schematic, you can see here that the PAN fiber is there. Okay. So, the first the PAN fiber is being made, precursor fiber is being made, and then it goes through a stabilization process. In the stabilization process, basically oxygen atoms gets attached with the PAN structure, and we are calling it stabilization because I will be showing you the internal atomic structure, molecular structure, and you will be seeing that because of the addition of oxygen atoms, the PAN structure becomes rigid. Why do we need a rigid structure here? Because the next steps, which are carbonization and graphitization, are high temperature steps. At those high temperatures, we want the PAN structure to to be stable, and because of that this oxidation step is actually applied, which we are calling as stabilization process. So, the PAN fiber is made first, which we are calling fiberization, then we have oxidation process at around 250 degrees Celsius to stabilize the PAN structure, and then it goes through multiple furnaces, and in these multiple furnaces the temperature is slowly raised from 250 degrees Celsius to 1500 degrees Celsius and ultimately around 2500 degrees Celsius, right. So, basically in the third stage, where it is, which we are calling as carbonization, here basically the basic purpose or basic aim here is to basically get rid of the non-carbonaceous elements in the form of different kind of gases like HCN, CO, CO2, hydrogen, nitrogen, so that we get rid of the non-carbonaceous elements, and finally you get a very kind of hexagonal structure of the graphite. So, then you go for a higher temperature. Okay. So, here even if you get rid of the carbonaceous material or carbonaceous non-carbonaceous elements, you may not get all the hexagons. Okay. There could be heptagon or pentagon. Okay. So, basically to get rid of those structures, those structures which are not hexagons, okay, this high temperature process or graphitization is being applied. Okay. Let me give you or show you the molecular structure and the change in the molecular structure, and I think it will be more clear to you. So, if you look at the PAN structure or polyacrylonitrile structure, it is like this. Okay, CH2, and then you have a nitrile group attached alternatively. Okay. The idea during stabilization or oxidation is that you attach oxygen atom like this, so that it becomes a rigid ladder structure. Okay. So, you can see here this is the initiation step of making hexagonal structure, right, and then in the latter stage of carbonization and graphitization is basically to get rid of this nitrogen, oxygen and hydrogen. So, you can see here, okay, this oxidized polyacrylonitrile ultimately because of carbonization and graphitization gets a perfect graphitic structure or a graphene structure with hexagonal rings where the carbon atoms are only present. Okay. So, that is the basic synthesis technique of carbon fiber, where the precursor is PAN. Similarly, you can look at the mechanical properties of PAN fibers. So, you can see here, as I mentioned earlier, it is very interesting to note here is that how you synthesize or what is your synthesis final synthesis temperature. Based on that, or in other way, how perfect is your graphene structure, how perfect is your hexagonal structure. Based on that, you have wide range of tensile strength and modulus, from low strength, low modulus to extremely high strength, high modulus. And based on your application, okay, for example, if you need this kind of aerospace applications where you need very high strength and high modulus, then you choose this kind of carbon fiber, and vice versa. Okay. That is how you produce your carbon fiber. Okay. And just to give you another example, pitch is again another precursor. So, source of pitch are basically PVC, polyvinyl chloride or petroleum asphalt or coal tar. There are different kind of precursor material, and the same process is adapted in making carbon fiber. So, you go for spinning to get a fiber, and then stabilization process, and then carbonization and graphitization. Okay. So, I am not going into details of all these things, because already I have discussed the 4 stages. Okay. Now, let us quickly look at the properties. Okay. So, what you see here is that based on again the there are 2 parameters here, 2 affecting parameters. One is what is the precursor material, and then at what temperature ultimately the carbonization and graphitization was done. Okay. So, for example, you can see here you can have rayon or PAN, okay, and then or pitch as well. So, you can see here, let us consider about this pitch. Okay. So, low temperature heat treatment, high temperature heat treatment. You can clearly see that the modulus, in fact, if you look at this particular one mesophase pitch, the modulus is actually changing from 340 to 690 as you go for higher temperature, right. And obviously, the resistivity also changes according to that. You can see here it becomes more a graphitic structure, or it goes towards perfect graphitic structure, and that leads to decrease in the electrical resistivity. Okay. Similarly, for rayon and pan, you can see based on the precursor material, you can see the modulus and the electrical resistivity varies. Obviously, if you compare with single crystal graphite, obviously these are single crystal graphite. So, these are perfectly hexagonal structures. So, strength is basically theoretical strength. Okay. It is like 1 TPa strength. So, it is quite high. Ideally, this is ideal values, okay, but in reality you do not go reach to that high value, but still you can see here the modulus can easily reach in the range of 600 to 700 GPa. Some more comparison in terms of the carbonization temperature. So, you can see here there are 4 steps have been shown here, or 4 classifications have been done. If you are heating to 1000 degrees Celsius, 1000 to 1500, and then 1500 to 2000, and then above 2000 is graphitization. Okay. So, from low modulus to standard modulus to very high modulus you achieve depending upon the temperature of graphitization, from 200 to you go above 325. Okay. Just to compare with high strength tensile steel, high tensile steels, obviously the modulus and specific strength. So, you look at the specific strength is quite high because of the low density. Okay. All right. So, with that I would like to conclude this particular class. So, basically initially we discussed about boron fiber synthesis, we discussed about the properties, synthesis and application. So, in case of boron fiber, you can see here the UTS is extremely high in the range of 3 to 4 GPa, modulus in the range of 400 GPa, melting point again very high above 2000 degrees Celsius. So, because of this high strength, high modulus and high melting point or high temperature material, this boron fiber and also the density is quite low, mind that. So, based on all these factors, boron fibers are exotic fibers, we can say, which can be used in advanced applications. Okay. So, boron fibers, just to mention it once more, boron fibers are synthesized by CVD method, chemical vapor deposition method, by reduction of boron halide, and we also discussed about concept of critical temperature. So, in this case tungsten wire is used as the core material on which boron gets deposited, and during synthesis of boron fiber there has to be a tight or close relationship between the wear speed and the temperature, and which we are calling as concept of critical temperature. And then the next one we discussed about carbon fiber. So, we discussed again the properties, synthesis and application of carbon fiber, and the basic steps as we discussed in synthesis of carbon fiber are there are 4 steps. The first step is the fiberization of the precursor material, and then the stabilization of the precursor material or oxidation of the precursor material, and then high temperature steps like carbonization and graphitization are done, and depending upon what kind of temperature, final temperatures of synthesis and what kind of precursors, we get a wide range of properties in case of carbon fiber. But we can safely say that we can easily achieve young modulus of around 600 GPa and UTS in the range of 4 GPa, and obviously the density is quite low. So, this is a very this is one of the suitable material, most suitable material for fiber to be used in case of high structural strength and modulus application. So, what I plan to cover in the next is that, as we were talking about fibers, I want to talk about some more commercial fibers. So, in the next class, I will talk about aramide fiber and ceramic fibers, their synthesis, application and properties. And I thank you all, and I will meet you all in the next class. Thank you again.